Hey everyone, welcome to chapter 5, which is about cabling. And in this chapter, we are going to uncover the secrets behind the wires hiding under your desk and the walls, and sometimes in that mysterious ceiling space that no one wants to get into. Cables are like the veins of a network. Without them, the data doesn't flow. By the end of this chapter, you'll know how cables work, which ones to choose, and how to fix them when they go rogue. Think of this as like cable therapy, but with less crying and more diagrams. Objectives of the chapter. By the end of this chapter, you are going to be a wizard of cables. We're going to cover 4 main objectives during this chapter. First, we'll explain the basic data transmission concepts. Think of that as an understanding of how your cat videos actually travel through the internet. Second, we'll describe various types of network cables and their connectors because, not all cables are equal. Just like not all pizza toppings belong together. Pineapple. Third, we'll compare the benefits and limitations of different networking media. Spoiler alert, fiber optic is the sports car of cables. And finally, we'll learn to use the right tools to troubleshoot cable problems because sometimes you need more than just turning it off and back on again. So here we go. Before we get into cables, let's talk about transmission basics because, networks are complicated highways of information. Sometimes traffic flows smoothly and sometimes it's like rush hour with a pileup. Transmission basics are the traffic laws of data. They help us measure efficiency and figure out why things slow down. For example, if your Wi-Fi feels slower than a snail on vacation, chances are there's something interfering or clogging the data highway. So we're going to break down the measurements and the obstacles that get in the way. Some terms we're going to get into. Frequency. Frequency is basically speed. It's the number of times a signal flips per second, and it's measured in megahertz or gigahertz with the abbreviations there. Bandwidth. Bandwidth is like the width of a highway. It's how much traffic could fit all at once. Throughput is reality. So that's how much traffic actually makes it through when you factor in construction, potholes, or your neighbor binging Netflix in 4K. Technologies like modulation and encoding are like carpool lanes because they squeeze in more data without expanding the road. So the question is, what causes issues with our data? First, we've got noise. Noise is kind of like that noisy neighbor that degrades or distorts your signal. Two of the most common troublemakers are EMI and crosstalk. EMI, which stands for electromagnetic interference, is the noise from things like your microwave, the fridge, or even a copier. It's basically electronic static. Crosstalk is when the signal from one wire messes with the signal on a wire right next to it. Think of it like a whisper from your friend that gets picked up by someone else's ears. Alien crosstalk is when this happens between two different cables, and if it happens right at the start of the cable, it's called near-end crosstalk. If it happens at the end, it's far-end crosstalk. So it's just like a whole bunch of interference. Next, we have attenuation. And that is when the further a signal travels, it loses its strength the further away from the source it gets. So think about like if you're on a football field and you're yelling across a football field, your voice will fade before it reaches the other side. That's why we use things like repeaters, and that would be like giving your message a megaphone. and yelling across the field. The other thing we have is latency. Latency is the delay in getting a response. Have you ever texted someone and then like 5 minutes later they just reply with the letter K? That's latency. Drives me up a wall, but that's latency when you're looking at it in these types of terms. Cables do add some latency based on their length and how many devices the signal has to pass through. Next, we have RTT, which stands for round trip time, and that measures how long it takes a packet to go there and back again, kind of like a digital boomerang. If packets come back at different times or out of order, that's called jitter. For example, if you're video chatting and suddenly the other person's face freezes or their voice sounds like a robot, it's probably jitter. The network's rhythm gets messed up and your smooth conversation kind of turns into a remix. Next, let's look at traffic flow, and this has to do with your NIC settings, your network interface card, because that's really what determines how signals travel over different media. Full duplex is the first term, and that's like a two-way street where traffic flows in both directions simultaneous. So that's like cars going north, cars coming south, and they're going at the same time without ever crashing. Half duplex is like a one-lane bridge where traffic can go in both directions, but only one at a time. So like a drawbridge or something, where you can go and then stop, and then the other group comes and stops, and there's a wait in that process. Simplex is a one-way street where traffic only flows in one direction and not the other way. So think of this. Think of simplex like a water slide, just one direction, down. So here's what it looks like in real life, and we're looking at a device manager network adapter configuration in Windows, where it shows you that you can actually change your speed and duplex settings. It's like switching between different driving modes in your car. If you've got one of those types of car, you can go like economy, sport, snow, weather, extreme, just get me to work on time mode, whatever your car may have. And most modern networks use full duplex. So let's actually get into cabling. And we're going to start with the oldie, or the OG, so they say, which is coaxial cable, but you probably just call it coax. Coax was king back in the 80s and the 90s. And if you have Charter, you know what coax looks like. It's that thick cable with the metal pin in the middle. If you've ever peeled it back, it's like an onion. It's got this metal core, it's got some white insulation, it's got some silver shielding, and it's got that black outer jacket. And nowadays, coax is mostly used for cable, internet, and TV. RG6 is common for most modern setups, but there is some RG59 still out there, and that's older and it's weaker. Coax does get connected by those two connectors there. The F connector, which is kind of your traditional screw-on, and then B and C, which is a little bit different. It kind of, you push it on and then you twist it once in like a quarter turn and it locks in. So next we have twinax, which is similar to coax, but it's got two cores working together. And that teamwork lets it handle higher speeds. Twinax is tough, it's flexible, and it's used in short, high-speed connections like in a data center. And for this, think of like coax as a single-lane road. You have one lane of traffic going one direction. Twinax is like two-lane road, and it's got better pavement. So you get twice as much going on and a smoother ride, so to speak. So here's a picture of what the coax and twinax looks like. This is actually twinax. So this is what it looks like on the inside. Notice it's got 8 core pairs with braided shielding and foil. Um, it's like each pair of wires gets its own bubble wrap in there, that all that shielding and protective coating. This sophisticated design is what allows TwinX to handle high-speed data transmission while staying tough enough for data center environments. Now we're getting to kind of the star of modern networking, which is the twisted pair cable. This consists of color-coded insulated copper wire pairs. Each wire, as you see, is about 0.4 to 0.8 millimeters in diameter, which is thinner than a standard paper clip. Every two wires are twisted together, and it's all encased in a plastic sheath. Some people may ask why it's twisted, and it's because twisting actually helps cancel out interference. It's like noise canceling headphones for your data, really. And Ethernet networks typically use 4 wire pairs. Fast Ethernet uses 1 pair to send and 1 to receive, like having separate lanes for that incoming and outgoing traffic. And Gigabit Ethernet uses all 4 pairs for both directions simultaneously. Now that's like having 4-lane highway where traffic flows both ways on every lane. Twisted pair cables come in different categories, kind of like movie ratings, but for the speed of your data. There's category 3, 5, 5E, 6, 6A, 7, 7A, and 8 as of now. Modern LANs use Cat 5e or higher. Anything lower is like trying to stream Netflix on dial-up. Now, if you don't know what dial-up is, when I was in college, when the internet came out, 95, 96, you used to have to connect to the internet with a modem, and it would actually dial a phone number, and it would ring, and then it would make all this garbly noise, and then you would connect to the internet that way. And if anybody tried to call you, it would ring busy because you were on the internet. So I feel old after sharing that. So all twisted pair cables fall into 2 camps. We've got STP, which is shielded twisted pair, and UTP, which is unshielded twisted pair. STP, kind of like wearing a raincoat in a storm. Okay. UTP is kind of like going out into the storm with no raincoat, just regular clothes. One protects you a little bit more than the other one, obviously. So this is what a Cat5e data cable looks like. Okay, notice the labels printed right on the cable, tells you what kind it is, so you know what you're dealing with. And then this one, I think it says Cat5e and UTP. That printing is kind of like the labels for food, the ingredients of what's inside there. And on the ends there, we've got RJ45 connectors. That's the standard connecting connector for data cables. You've probably used these. You probably have many of these in your house or work. You just may not have known what they were called. So digging in a little bit deeper with regards to the actual cables inside of those Cat5 cables or Cat5e or whatever version you're on, they're individually insulated. They're surrounded by metallic shielding, which is usually foil. The shielding acts like a bodyguard for your data. It protects it from the extra electromagnetic interference that EMI, and the effectiveness depends on several factors. And those factors are the volume and the type of environmental noise you have going on, and the thickness and material of the shield, and how well it's grounded, and the symmetry and consistency of the shielding as well. So in this situation, it's like trying to choose the right umbrella for different types of storms. If it's just barely drizzling, you may put a hat on. If it's raining a little harder, you'll have a little bit bigger umbrella. If it's raining really hard, you may have this big old golf umbrella. So this is what the inside of a Cat5 cable looks like. This is the anatomy of the shielded twisted pair. Notice the jacket and sheath on the outside. Then you have foil sheathing. Then you have the braided copper shielding and the 4 twisted pairs inside. So, if you've seen those Russian nesting dolls where you keep opening it and it keeps getting smaller and smaller, that's kind of what this looks like. Now, modern cables like the Cat 8 take shielding to the next level because it has a more sophisticated material. It's got more tightly twisted wires and it can handle higher bandwidth. That's kind of like comparing the modern smartphone to the original brick phone. Now, when my wife and I started dating back many moons ago, her parents had one of the earliest cell phones, and you had to carry like this big old suitcase type thing, and the phone was ginormous. And that's kind of like what we're comparing this to. We're comparing that old phone to your iPhone and your fancy Samsung you have. Okay, the unshielded twisted pair is a little bit different. Okay, this is kind of it's more common. It's budget friendly. It consists of insulated wire pairs in a plastic sheath without additional shielding. Now, this makes it less expensive and easier to work with, but also less resistant to noise than the STP. And it's kind of like you get what you pay for. Historically, UTP was more popular because of cost, but the modern STP prices have become more reasonable. So think of it like how the flat screen TVs used to cost a fortune, but now you see them everywhere, and you've probably got multiple sizes of them in your house. Both STP and UTP use RJ45 connectors and data jacks. They're compatible with the same equipment as well. They also get the job done. I mean, they both work. They're just kind of suited for different situations. STP is more expensive, but better at handling noise. UTP is cheaper and easier, but it's less protected. If you're wiring a home or office, UTP is usually fine. If you're wiring a factory floor next to a giant motor, then STP would be the smarter choice. Now, when you're terminating this cable, it's very important that it's terminated correctly. Otherwise, you're not going to get any kind of communication. So it's like trying to get your puzzle pieces put together, and they're not necessarily fitting. If you don't put them in the right way, you're not going to have cross communication there. Terminating something poorly can cause signal loss. It can cause noise, and it's going to give you some issues. The TIA and the TIA/EIA, and you've got two different modes there, the 568A and the 568B. You can use either one, but the important thing is that whichever one you choose, and there are different ways of putting the wires into the connectors, you have to make sure you use the same way, the same method throughout your entire network. So if you want to go with the A method of terminating and inputting your jacks, you can do that, but don't then switch to a B because you're going to have some issues. If you try to mix it, you're going to have problems. It's like starting in English and then converting to Spanish or whatever. It's not going to be very productive. So this is the actual wiring schematic of both different styles of wiring. You've got basically the orange and the green pairs swap positions between the two different types of standards. The table below that shows which pins handle the transmit, which pins receive, and which pins are bidirectional for fast Ethernet and gigabit Ethernet. It's like having different languages that say the same thing. Both work perfectly, but everyone involved needs to speak the same language. So, the three main types of cables that you're going to encounter. The most traditional type is called a straight-through cable, which is also called a patch cable. Both ends have the exact same termination. They both have A or they both have B. These types of cables connect different types of devices, like computers to switches. Crossover cables will have transmit and receive wires, and they're reversed, and they connect like devices. So if you're connecting one computer to another without a switch, you can use that crossover cable. And then finally, you have rollover cables, which is also called console cables. And those are used to connect computers to router console ports with all wires reversed as a mirror image. So that one's like having different keys for different locks. Each cable has a very specific purpose. This right here is your cheat sheet for Ethernet standards. So we've got the 10 base T running at 10 megabytes per second over Cat3 cable, all the way to the blazing fast 40G base T pushing 40,000 megabytes per second over Cat8. So that's like going from your 10-speed bike all the way to like a rocket. Notice the higher speeds require better cable categories, and the maximum distance per segment stays at 100 meters for most standards, except the 40G base T, which maxes out at 30 meters. So you're looking at around 300 feet for most things, and then somewhere around 900 feet for the big dog. That's just to compare it. That's like having your higher performance cars needing to run premium fuel. If you've never had to run premium fuel in a vehicle, you're probably not buying high performance cars. Better performance means better materials. Now we're going to transition a little bit to PoE, another acronym, which stands for Power over Internet, or I'm sorry, Power over Ethernet. It would be POI if it was the other way. And PoE sends both data and power over the same Ethernet connection, over that cable. The IEEE 802.3 AF standard provides 15.4 watts for standard PoE devices, while PoE Plus, which is 802.3 AT, bumps it up to 25.5 watts, so you can get a little bit more power. PoE defines two device types. You've got power sourcing equipment, PSE. These are like the power providers. Then you also have PDs, which are the powered devices. Those are the devices that actually receive power. And this situation is like having electrical outlets built into the network cable. PoE requires Cat5 or better copper to handle both data and power safely. Here's a diagram of how PoE works in practice. The top setup there shows a PoE switch directly powering a security camera through a single cable, which means that data and power are going together. The bottom shows how to add PoE capability to a non-PoE equipment. Excuse me. Using, you can see there's an injector and a splitter. So this situation is like adding adapters to use newer plugs in older outlets. PoE is perfect for security cameras, wireless access points, IP phones, and other devices that need both network connectivity and power, but might be installed in hard-to-reach places. Next type of cable we're going to look at is fiber optic cable. So in fiber optic cable, instead of electrical signals, it uses light pulses to transmit data through glass or plastic fibers. Data travels via pulsing light from lasers or LEDs. So that's like sending Morse code with a flashlight, but millions of times per second. Okay. The core is surrounded by cladding, which is a different type of glass, then a plastic buffer that absorbs escaping light, and finally Kevlar strands for strength. And yes, it is the same Kevlar that's used in bulletproof vests, because fiber optic cable doesn't mess around. Here's what fiber optic cable looks like. Notice how you can see each individual fiber strand. Each of those hair-thin strands can carry an enormous amount of data using light. It's like having a highway where cars travel at the speed of light. Fiber optic cable really is the superhero of networking, because it includes extremely high throughput, excellent noise resistance, great security, although it's not perfect, and the ability to carry signals over long distance. There are a few drawbacks though. It's more expensive than twisted pair cable, and it does require special equipment to splice and terminate. So this is like comparing a Ferrari to a Honda Civic. The Ferrari performs better, but you'll pay more for it because you're going to need specialized mechanics. When we're looking at fiber, we're going to start with looking at single mode fiber. Single mode fiber is like the Lamborghini of fiber optics. It has a narrow core, which is around 8 to 10 microns, which is thinner than human hair, and laser light that travels in essentially one path with very little reflection. Because the light doesn't bounce around much, it doesn't disperse as it travels. SMF can handle the highest bandwidths and the longest distances of any wired transmission media. I mean, hundreds and hundreds and hundreds of miles. The internet backbone depends on this type of cable, but it's rarely used for short connections because it's really, really expensive. So this is like using a Formula One race car to run to the grocery store. It's overkill, but it's pretty impressive. Next type of fiber we have is multi-mode fiber, MMF. This is like the single mode fiber's affordable cousin. It has a larger core diameter than SMF. The light pulses travel at different angles through the fiber, which is why it's called multi-mode. And that causes more signal attenuation than single mode fiber. But it's still excellent for many applications. Common uses for fiber include connecting routers and switches and servers on network backbones and connecting desktop workstations to the network. In my area, in a school district, we have fiber that runs between our schools and our buildings. Then we also have fiber that runs from our MDFs into our IDFs because of the speed. So single mode fiber is like a first class airline travel, and multi-mode fiber is like business class or coach. Both get you there, but one costs more, and one does offer you kind of like a premium service. Now, fiber connectors are classified differently than copper connectors. MMF connectors are classified by the number of fibers they connect to, while SMF connectors are classified by the size and shape of the ferrule. And the ferrule is the extended tip of a connector that makes contact with the jack. SMF connectors typically come with 1.25 millimeters or 2.5 millimeter ferrules. And the most common 1.25 connector is called the local connector, or the LC, while the popular 2.5 connector is the SC and the ST, which is the standard connector and the straight tip. So this is like having different sized USB ports. They all serve the same basic function, but they require the right connector for the right port. For MMF, the MTRJ connector is common and handles multiple fibers in one connector. But the real star is the multi-fiber push-on, which is the MPO, because that supports both MMF and SMF, and it usually contains 8, 12, or 24 fibers. Some can have like 32, 48, 60, or even 72, but they're typically 8, 12, or 24. So imagine having dozens of data highways in a single connector. That's some pretty serious bandwidth there. When you have fiber transceivers, and they're like the universal adapters for fiber connections. Some switches have sockets where you can plug in different types of modular interfaces called transceivers. To avoid compatibility issues, you must match transceivers based on the speed and protocol, kind of like making sure your phone charger matches your phone, really. Installing a transceiver is usually as simple as sliding it into a compatible socket. Most come with tabs or latches and are keyed so that they only fit when aligned properly. So here's a look at the key fiber Ethernet standards. We have a 100 base SX, which uses short wavelengths, about 850 nanometers, and that's for gigabit Ethernet, and that's kind of like the short range option. You have 1000 base LX, which is more common and it uses longer wavelengths, and you can see that it's at 1300 nanometers. And this is used for greater different distances. Can't talk. And then for the 10 gigabit Ethernet, we have 10 G base SR for short range and 10 G base LR, which uses 1310 nanometer lasers for long range. The wavelength numbers might sound like science fiction, all those small numbers you've got there, but they really determine how far and how well that light travels through that fiber optic cable. Every fiber does have challenges, just like everything else we do in networking. There can be a fiber type mismatch, and that's really about core diameter differences. Even the same mode cables can be mismatched if cores have different widths. It's like trying to connect a garden hose to a fire hose. Not going to work. Wavelength mismatch occurs when transmissions are optimized for one cable but sent over via another cable. That's like me speaking English to someone who only understands Spanish. No bueno. And then also dirty connectors is a common fiber problem, and that causes signal loss and it can cause errors because they really, really need to be clean. And I'm talking like hospital operating room clean. And then lastly, we have link loss, and that happens as the light signal loses power as it travels from one end to the other. Even light gets tired sometimes, eventually. So, cable troubleshooting tools. First, you need to start troubleshooting by checking the LED status lights on your network connections. Obviously, a steady light means connectivity. A blinking light shows activity, or a red and amber lights are really kind of a cry for help. When you suspect cabling issues, you need the right tools to analyze and isolate the problems. It's like having a medical kit for sick networks. You really need the right instrument for the right diagnosis. So let's talk about some of those tools, okay? The first tool, and it's kind of the best friend here, is the toner and the probe kit. A tone generator, which is called the toner, sends a signal on a pair of wire, while a tone locator, which is the probe, detects that signal and makes a noise when it finds it. Together, they help you trace cables and determine where wire pairs terminate, which is very important when you're especially dealing with, a ton of cables that all look the same. However, they can't determine the cable characteristics like speed capabilities. Think of them as like bloodhounds that can track cables, but they can't tell you how fast they can run. Next tool that's important is the multimeter. The multimeter is really the Swiss Army knife for electrical testing because it can measure everything from network wires to your wiring in your house to motor vehicle wiring. It measures resistance, voltage, impedance. It helps you verify that your cables conduct electricity. It can check for noise in the line, and it can also test for short or open circuits. So just quickly defining that, a short circuit is no good. It's an unwanted connection. It's like having a leak somewhere. It's not something that you're going to enjoy. An open circuit is a missing connection. It's like a bridge with a gap in the middle. So you see them when they build bridges, and then they stop, or the last piece is typically the middle piece. So think of those bridges being built from both ends of the shores, and then right in the middle, it's not full. That's that open circuit. And that's obviously going to be an issue when it comes to transmitting signals through your cables. You also have a cable continuity tester, and that checks whether cables can carry signals from point A to point B. So basically, like, does this cable work? Um, Copper cable testers have two parts. It has a base unit that generates a voltage and a remote unit that detects it. Most provide lights or audible tones for pass fail results. Green typically means good. Red means time to buy a new cable. Some can verify that UTP and STP wires are paired correctly, and they can detect if they're reversed, crossed, or split. Having something like this is like having a quality control inspector for your cables. Next is a cable performance tester. This is like a continuity tester on steroids because they can help measure distance to cables. Distance to devices or cable faults. So either does it get there or is there a break somewhere? You can also measure attenuation and crosstalk, which is also called next. It can check termination resistance. It can check impedance. It can issue pass fail ratings for Cat 3 through 7. It can store and print results, and it can even create graphical reports of problems. So this is a big dog here. Very important and very helpful. Using this is like getting a full medical checkup for your cables instead of just checking to see if it has a pulse. So you're going to get more of a story of what's going on with your cables using this as opposed to something previously discussed. Continuing with cable testing, we've got an acronym called TDR, which stands for Time Domain Reflectometer. What that does is it sends signals and measures how they bounce back, kind of like sonar of the network. It can tell you distances between devices and whether terminators are working properly. And then you've got OTDRs, which stands for Optical Time Domain Reflectometers. And it really does the same thing for fiber cables. It measures length, locates breaks, bad splices, or bends. So OTDRs are kind of like your detectives of your fiber optic cables. It can pinpoint exactly where your problems occur. The problem is they're very expensive. So in order to be really precise, it's going to cost you some money. Next, we have an optical power meter or an OPM. That measures how much light power is transmitted on fiber optic lines. It's kind of like a light meter for photographers, but for network cables. The OPMs must be calibrated precisely following strict optical powered standards. Room temperature, connection type, and technician skill all affect the results of using one of these. Fiber optics demands things to be very, very precise. We've said that multiple times. If you want it to work correctly, then everything has to be nearly perfect. It's like, trying to cook a really, really, really nice, fancy meal and not really following the recipe and just kind of throwing it together. That's not going to work. The recipe needs to be followed to a T if you want the results to be the way that they are expected. So we made it, the end of chapter 5, 38 minutes and some change, going to be 39 minutes. So we have completed our journey about network cabling. You should now understand basic data transmission concepts like frequency, bandwidth, and the various gremlins that can mess with your signals. You should be able to describe different cable types from old school coax to futuristic fiber. You know which connectors go with what cables. You can compare the benefits and limitations of various networking media, whether you need the reliability of fiber or the affordability of UTP. And finally, you've learned about the tools that can help you troubleshoot cable problems, from simple toners to sophisticated OTDRs. That's it for chapter 5. I will see you next for chapter 6.